Okay, first for orientation, this is going to be an experimental talk. For those of you who saw the last 3 talks I gave last week, this is not going to be a surprise. This right now is what a quantum computing type machine looks like. I think this one is actually fake. This is like a publicity machine from IBM, but what it really reflects here, in the middle in these cryogenic magnetic shields lives some kind of 50-bit quantum computer. All this other stuff, the majority of the volume and a lot of the expense of the system is 50 or so readout channels, because for every quantum bit in your system, you have to have real-time, highly fidelity QND readout for some kind of machine that's going to have a chance of working. So the point of today's talk is to sort of tell you about 2 projects that are still in progress, and the basic assumption that underlies it is somewhere, we're not going to talk about it, and it's not our problem for today, there's some qubit or resonator or cavity system which has had some quantum light impinged on it, entangled with it, and now this is where we come in. We want to amplify this pulse. We want to route it to another qubit cavity system. We might like to interfere it with another pulse in the way I showed last week. And the key limitation to any of the hardware we build right here is that this is quantum light. To get the most out of it, we need quantum efficient hardware. We need quantum mechanics to continue down the story through these engineered systems that are going to process and manipulate this quantum information right here. So the key limitation is how quantum efficient is your system. And the solution is basically parametric amplification. So today's talk is going to be talking about engineering tools that try to implement driven, damped, open quantum systems that can play fun games with light in the service of this overall vision of quantum computing. So first, one more time, just a few details about the parametric amplification that's relevant for today. And then the meat of the talk is these 2 conversations, one about the effect of higher order terms in your Hamiltonian, and the other one is about the use of parametric drives. So again, maybe the usual coupling we're used to between 2 systems, so this could be 2 spins or 2 harmonic oscillators, is something like direct exchange, where they tend to swap photons. If the 2 cavities or qubits are at very different frequencies, exchange doesn't happen anymore. Basically, there's an energetic penalty that stops a 5 gigahertz photon from swapping to being a 7 gigahertz photon. If we now have a bigger system now with 3 modes, what we can do is to take a 3-body interaction, for instance here, A, B dagger, C dagger, plus A dagger, B, C. So we have this extra C term on the end here. And if all 3 of these terms are very different, and in particular if the physical C mode frequency is very different than the difference, what we can basically do is drive this guy off resonance. We get a reduced effective 2-body interaction between the 2, so now 2 very off resonance resonators exchange photons as if they were direct contact with each other. And this is really nice because experimentally we can control the amplitude of the effective term by the drive, and we can also imprint on it, you see this complex phase here, which is going to be very relevant in the last part of my talk. So we have full control over the strength and the phase of this interaction. And there are sort of a growing zoo of different kinds of parametric interactions that we use in the laboratory. Today, there are really 2 that are relevant. Again, this first one, what we call it conversion, because it converts a photon from A to B. Again, we drive at the difference frequency here. It's far away from mode C. Now what you have is this effective 2-body interaction with this interesting conjugated phase, whether you go left to right or right to left. And what you get now is a device that has this conversion parameter C that goes from 0 to 1. And so what it basically does is if you set C to 0, the 2 modes are decoupled. If you set C to 1, it will absorb any light incident on this port. You see this 1 minus C goes to 0. And it will perfectly transmit it to the second port. So if we only look about, outside this device, if we only look about how light transforms as it goes through it, it is a noiseless photon converter. It will take a coherent pulse at one frequency, spit it out at another. It's very interesting. It's very relevant in the stuff I'll talk about a little later. Nobody uses this in the laboratory for anything right now. There are maybe some obscure uses, but it's hard enough to make these devices that no one is that interested in having this quantum efficient shifting in frequency. Nevertheless, we can make it. If we drive it correctly, you can see here almost perfect absorption on one particular port, here B, and then almost perfect conversion. That is that all of the photons into here. So it's not neutral in terms of power, but it's neutral in terms of photon number. All the photons incident on one port just swap to the other. More relevant sort of to everyday life is this other slightly different term, A dagger, B dagger, plus AB. So that tends to create paired photons in A and B. This is a gain-full process, so it tends to lead to phase-preserving gain. And again, the difference now is that you have a different three-body coupling, and you also have a different drive here. Now we're driving at the sum frequency instead of the difference frequency. But once again, if we look at what happens to light coupled into and out of these ports, any light incident on A is reflected with some gain root G, B the same. Again, now there's this conversion, but this time with gain, but with this same conjugate phase shift if you go one way or the other. So these devices are not, they're not non-reciprocal because I can't formally build an interference circuit out of them, but they have the seeds of non-reciprocity in them. Okay, and again, the gain is controlled by the pump power. I can set it to any value I want. Practicing in the laboratory at 30 or 40 dB is relatively easily achievable. And now here's some graph. Again, here's signal incident on one port, reflected with gain. Here's signal incident on one port and coming out the other port. So it works just like this. And this right now is the #1 sort of kind of use of parametric amplifiers to achieve gain. If it's not this interaction, it's a similar one, but the idea is that you get this parametric gain. And so the question of how you realize this physically, right, because nothing has been physically set up right now. In my mind, I always think about 3 modes. I work with electrical oscillators, so this is all drawn as inductors and capacitors. And we like some generic 3-body coupling, phi A, phi B, phi C. It could be something else, but we like this one for reasons I'll show you in a minute. If you rewrite that in terms of the raising and lowering operators, what I just have is some 3-body interaction strength, A plus A dagger, B plus B dagger, C plus C dagger. This works out and basically gives me all the potential 3-body couplings I could like between these modes. Of course, you don't see them if you don't drive the system with special pumps, because none of these things, if the A, B, and C modes are different, satisfy the rotating wave approximation. So what you have is that these kind of don't act unless you do something special. For instance, drive again at this pump sum frequency of A and B, and then that will basically pick out the relevant terms from the Hamiltonian here. The other terms are still there, they're kind of passive, and actually we'll use them later. We'll sort of use all these terms as the talk goes on, if we can get this generic coupling here. Physically, it's been implemented in Josephson junctions, optomechanics, diodes, optical fibers. It's a sort of very diverse set of experiments that use these couplings. In my case, it's all superconducting. So for superconducting, we only have one special object, the superconducting Josephson tunnel junction. Again, it's 2 electrodes of superconductor, an insulating barrier in between. It has a sinusoidal current that flows in response to the phase difference in the 2 superconducting order parameters across the junction, characterized by this critical current here and this sinusoidal current phase relationship. We're never going to switch the junction out of the superconducting state. We're always going to put a small current through it compared to the critical current here. And in that scenario, it really is a quantum object acting like a nonlinear inductance represented by this symbol X, with parameter Lj, which is the linear component of the inductance. And of course, this is also a capacitor. So just by itself floating in space, it's an anharmonic oscillator. And you can write its Hamiltonian down here and start to expand it out. This doesn't naturally have any 3-body terms, but we'll generate one in a second. And the point here of all of superconducting quantum information is that we can make these junctions very, very small. That means highly nonlinear, makes a qubit, or very, very large. You see there's a factor of 1,000 or more in difference in the size of these junctions. So today we're only focusing on the big junctions, making these weakly anharmonic devices that are going to be our parametric amplifiers and devices. What we make in the laboratory looks something like this. It's 2 lambda over 2 resonators. In the middle, ignore these central elements for a moment. What you see here, there are 4 junctions in this Wheatstone bridge configuration. And if I break the symmetry of the Wheatstone bridge by applying some flux through the loop, that will generate this generic 3-body coupling between this A mode of current, this B mode of current, and this C breathing mode of current. So I get exactly what I showed you on the theory slide. And actually I get a lot more than that. I get 4th order terms, 5th order terms, 6th order terms, and with some naivety here, what's typically done in the theory, if you look in this paper, is we just say they don't matter, right? We're hoping that we can truncate this series here, and this term is dominant, and this one is small enough that it doesn't matter. That turns out to not be true. So for reasons that'll become clear as the talk goes on, now we cross the ring with these linear inductors here. But the thing that powers the parametric part is just this 3-body coupling in the outer loop, which is the combination of this Wheatstone bridge shape and the applied flux that breaks the symmetry. Okay, so here's what they look. They're kind of commodity items. You can't buy my particular ones, but you can go to companies and buy these now. In the middle is the 3-body mixing element, too tiny to see with the eye. It has gap capacitors hooking it up to microwave transmission lines and cables, and you just put this in your refrigerator, you drive it with a pump, you get your gain. It's sort of straightforward these days, and the key thing, the reason that people care about these amplifiers in general, is that when we make them out of these pure superconducting elements that are very low loss and very well controlled, we get nearly quantum limited gain. So if eta of 1 means complete efficiency of information in your quantum system to information on your computer screen, we're at the 50 to 60% range, and this is huge. So that if we have some qubit, we can nicely read it out, and we can do more complicated experiments as I talked about last week. So this is the #1 virtue of these amplifiers. It's unfortunately accompanied by a lot of vices. So #1, this amplifier operates in reflection. You can't just hook it up to what you're measuring because it'll amplify your signal and send it right back down the same wire. You won't gain the information. So we have to have added external circulators, which is a pain, and they're bulky, and that was actually the majority of what you were seeing in that picture of that IBM quantum machine was external circulators. So we want to eliminate that. It has narrow bandwidth. In fact, the bandwidth of the amplifier is given by the bandwidth you started with divided by the gain. So the more gain, the more you ask from the amplifier, the less bandwidth it gives you. So we want to address that too. And now to get into the experimental sort of new part of my talk, the third limitation is gain saturation. This is actually not in the theory at all. If we just truncate at third order, we take the stiff pump approximation, there's no reason the amplifier should have limitations. Of course, in real life, the photon flux of the stiff pump is finite. And so what happens is the pumps both provides the sort of bias to the nonlinearity, but also the energy for amplification. So when you start to amplify a signal, you pull photons out of the pump, therefore the pump amplitude drops and your gain should drop with it. So you get this very generic curve right here, where for low powers it's unsaturated, for high powers it's saturated. The usual engineering figure of merit is just something that people find convenient, is to talk about the input power where the gain falls by 1 dB. And so actually exactly what's going on in this system is a little bit of a mystery now. So this pump depletion theory is the old one. It doesn't actually predict the behavior in our devices. It's much more optimistic. So what I'm going to show you next is basically one thing we figured out that is contributing to this behavior, but unfortunately there's still a little bit of a mystery here. So canceling higher order effects. So those Kerr terms, the fourth order terms that are basically pairs of number operators like A dagger A, or A dagger A, B dagger B, self and cross Kerr terms, it turns out are playing an important role here. If you just start again with your coupling and the stiff pump approximation, you should have no saturation. However, in our real devices, if your pump frequency is sort of at or a little bit above the sum of the pump frequencies, you get gain. And it kind of falls in this normal generic way we expect from our microwave textbook. However, if you go to negativity tunings, we get this very characteristic shark fin behavior, and it has no explanation within the pump depletion theory. And what we ended up figuring out and publishing last year is that what's going on is these higher order terms, especially the ones that don't involve the pump, so these three right here. What's happening is you're putting photons into the system, but it's moving out from under you. It's shifting to lower frequencies because these are almost always negative. And so what's going to happen is you try to put photons in, but it moves away, and in the end, this limits your gain. So that's what's going on here. And again, the theory responds pretty well. So we know that one major sort of experimentally observable limitation in these devices is Kerr effect. So we set out to fix it. Okay, so we looked now at several different sort of variations on this ring that powers the Josephson junction, powers the amplifier. So the canonical simplest ring is just no shunts at all. But when we look very carefully at the cross-Kerr and self-Kerr coefficients, we realize that the problem is that we are trying to go to a point of pure third-order nonlinearity and no fourth. So notionally, we would like to just move along this parabola here, and that would be a great place to sit. But because there are multiple energetic solutions for this ring, basically, you start to climb, and then you switch to another flux configuration, and you never make it high enough up to get to this null point, nor do you over here in the self-Kerr. So basically, there is no hope in this simple ring of ever finding an operating point where there is no fourth-order term. So then the way we made them in our laboratory for a long time, because it's easy, is to put Josephson junctions here in the middle. And this has some nice sort of engineering properties. It makes the device tune more easily. It's just a more practical circuit. That one, at first, looks good, because you see here now, because of the effect of these shunts on the overall stability of these now 4 loops, you can stay on this primary flux configuration until you reach the null. And this looks good until you look at the self-curve of the modes. Basically, these extra junctions add extra nonlinearity. They push you to a very negative starting place, and you basically never make it to the cross. So you can kill some of the Kerr terms, but not all of them. This basically is no help. These terms typically are about the same size. Killing some of them just leaves the other ones basically right where they are. So the solution we ended up settling on is something like this, just linear shunts here. So what we're really doing here is changing the physical nature of the circuit, trying to engineer a Hamiltonian that's more favorable to the open quantum system we're trying to make. And in that case, it finally works. Basically, there is no extra nonlinearity here. So just like the second solution here, the cross curves work, but now also the self curves work. And if we bias to these nice points, we can find points where there's 3-wave coupling and no 4-wave coupling, so that shark fin Kerr problem I told you about should just go away. There's a question, though, about how strongly to shunt. So how big should these junctions, or sorry, now inductors be compared to the Josephson inductance? So we call that parameter beta. And if you just solve the simple theory, you see that if the beta is too low, there's instability right at the coupling point. But if the beta is reasonable, there's a wide range where basically you hit the crossing point here where any instability or hysteresis in the system is far away. It sounds good until you try to build it. And what you realize is that this extra inductance around the outer thing, now that gets the term alpha, it's a little hard to see, it's the stray inductance compared to the inner inductance. In the devices we can build, it really eats our lunch, because it's really hard to meander these inner inductors and make them really big compared to these outer inductors, just from the geometry of the problem. And so what that does in real life is it pushes your cancellation points way out and pushes your hysteresis in, and the device is very unlikely to work because you have a very narrow parameter regime where this thing doesn't fail. So we were sort of dragged away from this design, and the solution is a little bit drastic. This is a false color SEM, but it also, at room temperature, you would notice, with your naked eyes, this is this buttery yellow niobium titanium nitride. This is our usual superconducting aluminum. The reason we're doing this is because we're making this a 10 nanometer thick niobium titanium nitride, and we're using its big kinetic inductance to boost physically the size of the center of the ring effectively compared to the size of the outside of the ring. And this allows us to push this alpha parameter, the stray parameter, down low enough that in the real laboratory, when we look at the A mode and, for instance, we drive the B mode off, strongly off resonance, we could nicely measure the Kerr effect. So this looks a little washed out. What you can see here, here's the flux in units of phase. Here's the pump power. If the system has a negative Kerr, it will get more red as you drive stronger. So you can see here's a negative Kerr here. If the system has a positive Kerr, it will get blue. So what we're doing here is just driving one mode in this case and looking how the other mode moves its linear resonant frequency. And now we can identify these cancellation points that we were hoping to see. So it really works in real life. And if we now instead just extract the slopes from this graph and plot for you the Kerr, you see we have a negative Kerr for most fluxes. But out here near 3 pi, we can come to the crossing point, and our evidence, I don't plot it here, shows that all of the relevant Kerrs cross more or less simultaneously, so we can really knock out the Kerr in our device. So this is very exciting. Here is the sort of standard graph. This red pimple-looking thing here is this fourth-order detuning shark fin characteristic effect. If we move to the cancellation point, the first news is good. There is none of this shifting. You see this curve is very flat here. And in fact, all the dynamic range curves are very similar, which is what we expect from pump depletion theory. The problem is it didn't actually get better. So this is open challenge number 1. Basically, we know that underlying this is some semi-classical or quantum dynamics. But the problem is we don't put usually into our theoretical solutions the things that make it don't work. Those are the things that make it computationally intractable. So clearly, there's more theory work that needs to be done here, because by engineering this one problem out of the device, we somehow have run into a problem that's either comparably bad, or maybe we've enhanced another problem, so we really get no help. That's not to say these devices aren't interesting in the laboratory, though, because now the next part of the talk is to talk about multiple parametric couplings. So here the idea is if I go back to now my system here with 3 different modes, what you really can do is sort of use every mode twice. You can drive this guy off resonance to couple these two, and still use the actual on-resonant response of the circuit as a signal processing unit. So you can basically have 3 couplings to the outside world. You can have up to, in this naive picture, 6 couplings. There's actually more, but at least 6 couplings of this conversion and gain kind. And basically, you can turn them all on at once. And this is where a lot of the excitement comes from in the field of parametric devices these days, but also a lot of the challenge. Because if you tell me a configuration of pumps and modes, I can calculate in a straightforward way their average response. So I can tell you, does it look like an amplifier or a circulator or so forth? But it doesn't work the other way around. I can't order a device from a theorist. It's still sort of guess and check, poke around in the dark, trying to figure out what's going on here. Nonetheless, we have these controls. We have the pump frequency, which selects which couplings we're activating. We have the pump strength. And crucially, remember, we have these funny non-reciprocal-ish phases that really were irrelevant in the first part of the talk. And so there are a lot of theory proposals about what we can do, and we work through them. But the overall idea, just one more time, is that with quantum efficiency in superconducting circuits, we can easily make passive and reciprocal elements. Basically, we just use superconductors. We open our microwave textbook. We build everything with low-loss elements. Everything is great. Gainful and non-reciprocal devices are much harder because the standard engineering techniques, including big magnets and yttrium iron garnets, are really not suitable for superconducting quantum-limited stuff. So we have to have our Josephson junctions, we have to have our sort of 3-mode multiply coupled devices and try to figure out how to work backwards from some ansatz here device here, or today, the other way around. And they need to be quantum devices, lossless, and the idea is that we're going to make some Hamiltonian who, when subjected to an open system, becomes the information processing unit that we like from Josephson junctions. Okay. I'm not going to really talk too much about the full 3-mode devices today. We've kind of taken a step back, but this has been experimentally realized by my old group at Yale, in a paper by Katrina Sliwa. The easiest one to wrap your head around is the circulator. So if you kind of think about photon hopping between 3 modes, we can control, if you like, the strength of the photon hopping between all 3, and we can imprint this non-reciprocal phase on them as we choose. So if you basically balance the 3 hopping amplitudes with the dissipation rates, and you balance the phase around the loop so that it adds up to, for instance, plus or minus 2 pi, then you have a system where a photon can come in, let's say from port A, and it can constructively interfere around to come out port B, and not the other way around. So if we look here, just a theory plot, here's reflection. At these 2 special points, you see the blue curves dip down, so the device is matched. No power bounces off, it all passes through to somewhere. And then in the one case, it all passes from A into B. In the other case, from B into C. So these are left-facing and right-facing circulators. It's a really nice device experimentally because even if your parameters are a little off, by changing the pumps around, you can basically always make it work out. And just by flipping the phase of one of these pumps by pi, you can really flip the sense of circulation. So it's really handy. But it suffers from some of these other problems, so they're not really in use yet, but I think they will be shortly. There are other variants of this circuit where instead of conversion on every arm, you add gain to get directional amplification, but this sort of suffices to just give a nice picture about how combining multiple parametric processes really gets you something special. The piece I want to focus on today, though, is something else. This is a coupling between 2 modes, but actually it's multiple couplings simultaneously between this pair of modes. So here we're going to pump at some frequency simultaneously with pumping at the difference frequency. If we balance the strengths, we can get this effective coupling Hamiltonian that's a 2-body A plus A dagger, B plus B dagger, so a quadrature to quadrature coupling between these 2 modes. And it turns out this is a really special basis proposed by Anja Medelman of Ash Clerk's group to build your multi-parametric devices on because it has very different behavior than the sort of standard 3-body term showed you before. The first thing is that it is not amplifying in direction in reflection anymore. It still has unity gain. We need to fix that with some more complications, but that's already a lot better. It's phase sensitive, which is interesting because basically the phase of this guy determines which quadratures get coupled together. So it's a phase sensitive amplifier in transmission, but it has really nice properties. First of all, the gain is no longer divergent. It's just linearly proportional to how hard you pump. That's going to turn out to be a good thing and a bad thing later. The other thing is that it doesn't suffer from this gain bandwidth limitation. Its bandwidth is always basically half the bandwidth you start with. So this is really exciting. There's one requirement that you have to match the kappas of these 2 modes. We don't find that particularly onerous in the lab. the one thing that's both good and bad about it, though, is that you have to pump really, really hard. So this is going to interact with this idea of higher order terms in the amplifier in a not so great way. Okay, and the problem we've had, and people have tried to implement this device before and failed, is again going to be these Kerr terms. And I'm just going to try to walk through a little picture of how they mess with the circuit and prevent you from biasing it up in practice. So the idea here is that we have our three modes. First, let's just turn on the the gain pump at the sum of the two modes. So if there were no fourth order term, you get reflection gain in the A mode and transmission gain to the B mode. If we drive from here, everything would be fine. This would be our coupling Hamiltonian. In real life, what the Kerr modes do is, again, they shift your frame of reference. And this is probably happening in every device in the laboratory. It's okay, the student didn't really know the A modes and B modes a priori anyways because of engineering difficulties. So he just turns the frequency around until he gets the gain at the right point where he likes it. The problem now is that we're going to also have to turn on a conversion process simultaneously. And so if you look now, here's a conversion process. Again, we can drive mode A. It'll be absorbed here. This is the coupling now, A dagger B, and transmitted to B. But now these modes shift the same way. And if you looked at the gain carefully, you would have seen that they shift opposite ways. So what happens is if you turn this device on, you sort of tune up one coupling, you tune up the other coupling, you turn them both on, the devices, you could maybe line up one part of this interference, but the other part is going to be disrupted. Basically, they'll shift away from each other. And it's a really devilish problem to find where you need to be in now this four-parameter bias space, because the amplitude of the shifts is dependent on the frequency, the power, and also where you drive, and now the shifts with frequency, and you just chase your own tail, and people have never really made this device work because of these Kerr terms. So now, though, with this niobium titanium nitride shunted rings we have in the laboratory, we can go back and revisit this idea and try to build this really nice interaction and see if it can actually work in the laboratory. And so that's what we did. Again, here's the theory. You actually have something that would be a big gain process and something that would be a really nice conversion process. You turn them on simultaneously, you get transmission gain, you get unity reflection gain, and again, this bandwidth here is very broad and should be a very powerful device. So this is what we want to see. And in these new fourth order devices, we really do see that, at least at low gains. So this is the best correspondence we've ever had with the theory. It really is behaving in the way we expect if we can kill this fourth order. So that's great. And that gives us a lot of hope sort of moving forward for the future. But the first thing we need to do is sort of really look at the device carefully. One of the things I told you is that it should have phase-sensitive gain. So here, this is a spectrum analyzer noise. So basically an integrated power measurement. So this is amplified quantum fluctuations. This is an input tone I put in. And because I see this symmetric and identical idler tone being generated, as I discussed in the tutorials last week, I know this is phase-sensitive. I can prove this by basically moving them very close together until they're only a hertz shifted away from the ideal input frequency here. And then what you see now, this is time, which is my proxy for phase shift. I see that again, I get gain that goes from positive gain to de-amplification and back again as I shift the phase of the pumps around. So this is working as a phase-sensitive amplifier as it's supposed to. If I normalize all the gains, I can see that for low gains, 5, 10, intermediate gain, 12 dB, the bandwidth is not changing. So it's really a fixed gain bandwidth device. So this has great properties. I'd like to turn it up to 20 dB. That's experimentally where we like to be with our gain and behavior in these systems. The problem is now when I start to get to higher gains like 16 dB, you see that this curve doesn't really match anymore and strange things start to happen. My theory doesn't really work anymore. And the device kind of falls apart thereafter. So why can't I get there? If I go back to this idea of fourth order cancellation, you start to get a clue. So here, in a singly pumped amplifier, here's the divergent gain profile. We've just normalized this to be 0. Here's the each pump profile of this quadrature coupling. And experimentally, it really sort of makes sense. But what you see now is that I'm now pumping each pump sort of 10 and 15 dB. So that's 10 or 20 times stronger than the ones before. So my net power in the system is something like 50 times what I used to have. And if I go back to these Kerr cancellation terms here, the bottom of the graph is what I showed you before. Again, here was positive Kerr, here's negative Kerr, here's the cancellation point between them. But you see if I drive sufficiently hard, I'm basically starting to see some curvature here. So there are even higher order terms in the Hamiltonian. And even though I was doing a good job of canceling them down here, by driving this much harder, I'm pushing them up again. They're all weaker in amplitude, they grow faster in power. So our best guess of what's going on right now is something like the 6th order term in our system is coming and eating our lunch and stopping us from getting from where we need to be. So as I said, these are sort of ongoing challenges, and we need to figure out sort of how to move forward in a more flexible way. We really are convinced that the future is more modes, more drives, really building these quantum information processing devices out of these really nice quantum engineered Hamiltonians plus parametric drives. And they work at the sort of model of toy experiments. They don't work well enough yet that I could convince anyone to use them in an actual experiment where you are not an amplifier designer. You know, none of my qubit computing brethren will adopt them because they're still just a little bit undercooked. One of the big challenges is that we need new theory tools. Again, we don't know what all devices are out there. We don't know the optimum trade-off between how much hardware, how much pump. We don't know what Hamiltonia sort of are benevolent and what are bad for us. One of the fears that David Pecker is working with us in collaboration also at Pittsburgh is maybe this idea of expanding in terms of sort of a Taylor expansion of harmonic oscillator terms, 2nd order, 3rd order, 4th order, is not good. Maybe the system is pathological and really it doesn't converge fast enough for us ever to be able to throw them away. If that's true, it'll be good to know it. I think this is an answer we hope to have in the 6 months to a year. But we're still going to confront this question of how we do better Hamiltonian engineering. In the meantime, we're also building better devices in the lab. We have some new microwave engineering tricks that will give us a better Hamiltonian. This is a funny system, right? This is where your fab is aimed at A's and A daggers. So it's really Hamiltonian engineering of these systems. So we think we can do somewhat better on that in the meantime. And in the medium term, really the outlook is to make something really more broadband, more high bandwidth, and directional for all of the computing and quantum information experiments that are going on in our field. Okay, thank you very much.
Questions? Any questions? I think people are gone to build up these kind of devices. What I was wondering was, like you said, more modes, more drives, better devices. Yeah. But what about the interaction between modes? Because that will complicate the physics behind it, right?
You mean the direct interaction between modes?
Yeah, direct interaction.
So the direct interactions are usually gigahertz away, and so those parts are detuned. The bigger problem is mode orthogonality, which is that you think these modes, really you're driving exactly A, but because of the imperfections, the asymmetries in particular in that diamond, you're driving A and a little bit of B. And so that, it's not the sort of terms that should be in the Hamiltonian, it's the interactions that show up because the modes are not really orthogonal like you expect them to be. That's the thing that gives us more concerns. And, you want to suppress that. I don't know, is 1% good enough? Is part per thousand good enough? Again, I don't know, because people like Ash Clerk, even though they sort of set milestones for us in terms of beautiful devices to build, they don't put in the bad parts. So we're still sort of looking for an intermediate theory sort of between the theorist and the experimentalist that's complex enough to capture the full behavior of the devices, but is not so bad that a full-time theorist is needed to calculate it. So that's kind of the point of this ongoing collaboration.
Okay. Yeah.
This is all within the paradigm of QND measurement. Yeah. Do you have to do QND?
Yeah, it depends on what you're trying to do. If you're trying to build a fault-tolerant quantum computer, yes, mostly. So there's always multiple ways around something in quantum mechanics. Your measurement doesn't have to be QND if you use ancilla. Practically speaking, we're already at the limit of sort of money and complexity to sort of do QND measurements. If you ask us to sort of double or who knows what overhead of extra bits so that we can trade in extra bits for non-QND measurement, it doesn't look very attractive right now. If suddenly making extra bits becomes cheap and easy, then yes, we'll make that trade-in. But right now, sort of everyone's experimental sort of financial trade-in, or trade-off really favors QND measurements of as few number of qubits as possible.
Even when you put in error correction?
Error correction makes the number of qubits so high that it really suppresses the appetite for adding even more. And the other thing is that the Q and D-ness really comes for free here. It's hard to imagine changes I make to the Hamiltonian of these devices or simplifications that would kill the Q and D-ness and still retain the really high quantum efficiency. And the quantum efficiency is really the name of the game, because most of the protocols for error correction or fault tolerance require 10 to the 4, 10 to the 5 measurements per error. So 10 to the minus 4, 10 to the minus 5 error rates. So these things are designed to be as pure a quantum Hamiltonian. I mean, they're dirtier than we want them to be, but they're still as pure a quantum device as we can imagine. And I think that tends to naturally lend itself towards Q and D-ness. So at least, again, I think my money currently is on Q and D over more qubits.
Okay, any more questions? If there are none, let's thank Michael Hatridge for a very nice talk. And we can proceed for lunch.